Welcome. Let's take a look at finding the antiderivative of x cubed minus sine of x dx. So we will be evaluating this indefinite integral. So using the linearity of the integral, we can rewrite this as the integral of x cubed dx minus the integral of sine of x dx. Now, to find the antiderivative of x cubed dx, this involves the power rule. And to find the antiderivative of the sine of x, that revolves around our knowledge of the derivative of cosine. Recall that the derivative of cosine of x is negative sine of x. So what this means for us is that if I want to integrate sine of x, my original function must be negative cosine of x. So if I take the derivative of negative cosine of x, that would be the negative of, because of the negative in front of the cosine, so it would be the negative of, now the derivative of cosine is negative sine of x, which actually would end up giving us sine of x. So when I take the antiderivative of sine of x, that involves the negative cosine of x. So we're going to get minus negative cosine of x. We'll have plus our constant of integration. Now, let's use the power rule for our first term. We'll have x cubed plus 1, so x to the fourth, times 1 over 4, or 1 over the exponent. So our antiderivative here ends up being 1/4 x to the fourth plus cosine of x plus c. Let's look at one more example. In this example, we have the antiderivative of 4 over 1 plus x squared. Now, this is a form that we should start recognizing. This is the same as 4 times the antiderivative of 1 over 1 plus x squared dx. And as we see down here, the derivative of the arctangent function is 1 over 1 plus x squared. So the integral, or the antiderivative of 1 over 1 plus x squared, must be the inverse tangent function. So it's tempting to try a variety of techniques to try and integrate this, but this is a basic form, and we must recognize that when we have the integral of 1 over 1 plus x squared, that is the inverse tangent function. So this would be 4 times arctangent, inverse tangent of x, plus c. Let's look at one more indefinite integral. In this case, we have the antiderivative of negative 2 over the square root of 1 minus x squared dx. Using linearity, let's pull that negative 2 coefficient in front of the integral symbol, and we have negative 2 times the antiderivative of 1 over 1 minus x squared dx. Now, if I recall what I know about the derivatives of inverse trigonometric functions, we know that the derivative of the arcsine is 1 over the square root of 1 minus x squared, which would mean that the antiderivative of 1 over 1 minus x squared would be the arcsine function. So this would be negative 2 times the arcsine function of x plus c. And I lost my negative there. Now there is another possibility here. Instead of bringing this -2 coefficient in front of the integral symbol, we could just as well have just brought the 2 and had 2 times the antiderivative of -1 over the square root of 1 minus x squared dx. And if we did that, then we could rely on what we know about the derivative of the arc cosine function. Its derivative is -1 over the square root of 1 minus x squared. So if I had the antiderivative of -1 over 1 minus x squared, that should be the arc cosine of x. So I could write this as 2 times the arc cosine of x plus c. Both are valid antiderivatives. I hope you find this helpful.